Good day to everyone. My name is Nur Anis Khalisa binti Jamawi and I will be one of the presenters for this video.
Hello, I am Harith Hakimi bin Saliman and I will be presenting alongside Anis in this video. This project was carried out under the supervision of Dr. Yusnita binti Johir, a senior lecturer in inorganic chemistry alongside her degree student Nur Atira Sofia binti Asmadi.
We are representing University Pendidikan Sultan Idris. The title of our project is Cubic Crysta Box, a 3D interactive learning model for crystalline solid structure. The Cubic Crysta Box model is a specialized teaching aid designed to help students visualize and understand the three-dimensional arrangement of atoms in cubic crystalline structures. It also supports learning and counting atoms within unit cells, making abstract crystallographic concept clearer and more accessible.
This model was developed using the AD Instructional Design Framework, which consists of 5 phases: analysis, design, development, implementation, and evaluation. Each stages ensure that the final product is effective, practical, and aligned with learning needs.
Students commonly struggle to understand crystalline structure because most teaching materials are limited to 2D diagram. Schools also place low emphasis on developing 3D visualization skills, making it difficult for them to imagine how unit cells and atoms are arranged in space. Research further shows that students have trouble connecting microscopic observation, submicroscopic atomic arrangement, and symbolic diagram, leading to confusion and misconceptions. These issues highlight the need for a hands-on 3D learning tool that makes crystal structures easier to visualize and understand.
The objective of this cubic Crysta box model is to help students visualize and understand 3D arrangement of atoms in each type of cubic crystalline structures using the cubic crystalline model, while also emphasizing the process of counting atoms within these structures.
Next, I would like to highlight what makes the cubic Crysta box unique and useful compared to the traditional teaching tools. Firstly, its uniqueness comes from its ability to visualize 3D atomic arrangement. This model physically shows how atoms are positioned inside the crystal, and students can combine multiple unit cells to see the complete structure. This makes abstract crystallography concept much easier to understand. Secondly, the model clearly demonstrates how one unit cell interacts with its 7 neighboring cells. This is something students usually struggle to imagine from flat diagrams, but the cubic Crysta box shows the division and interaction through the stacking of unit cells. Third, it accurately illustrates atomic position in SCC, BCC, and FCC structure. By placing atoms at the corner, face centers, or body centers, students can immediately see the difference between these 3 cubic systems.
In terms of usefulness, the cubic Crysta box model strongly enhances the learning outcome in crystallography. Unlike 3D traditional diagrams, this 3D model allows students to visualize atomic arrangement clearly, making abstract concepts tangible and learning experience more interactive. It also helps students understand atomic fraction, which are often confusing in the textbooks. By observing how corner, face-centered, and body-centered atoms are shared between unit cells, students can grasp this concept more intuitively. Finally, the model supports hands-on learning for counting atoms in a unit cell. By physically combining the shared fraction, students can determine the actual number of atoms in SCC, BCC, and FCC structures, reinforcing their understanding through active participation rather than passive observation. Topics such as SPT 1033, Solid Material Chemistry for Diploma. This topic covers crystalline and amorphous solids, unit cell, crystal lattices, and packing sphere. This model helps students to visualize the unit cell, packing arrangement, and atomic position, which directly assess their understanding of this concept. For the second one is SKT 3013, which is in organic chemistry for degree level. This course includes crystalline versus amorphous structure, unit cells, lattice point, Bravais lattices, packing spheres, coordination numbers, counting atoms in a unit cell, and X-ray diffraction.
The cubic Crysta box model consists of 3 simple components. First, the box, which represents a single cubic unit cell. This box acts as the framework that helps students visualize the shape and boundaries of the unit cells. Second, the polystyrene spheres, which represent the atom. These spheres can be positioned at the corner, face-centered, or the body-centered of the cube, depending on the structure being studied. Third, the Velcro tape,
which acts as the connector. It allows the atom to be easily attached, removed, and rearranged.
The Crysta Box instruction manual gives clear, simple steps on how to use the model. It helps students explore the unit cell, remove and combine atoms, and understand crystal structure through hands-on activities.
These make the model reusable and flexible, which is perfect for demonstrating different cubic structure such as SCC, BCC, and FCC.
Now, I will show you how to use the cubic Crysta box model. First step is to arrange 8 unit cells into a stack configuration to visualize how one unit cell interacts with its 7 neighbors. The second step is to identify atomic position within a single unit cell, where the atoms are at the corners, the body center, or the face center. The third step is to determine the atomic fraction by seeing how each atom is shared between neighboring cells. For example, corner atoms are shared by 8, face-centered atoms are shared by 2. The fourth step is to count the total atoms in one unit cell using this fraction. Students can combine or stack polystyrene pieces to form one complete atom. The fifth step is to find the total atom in the full stack model by multiplying the atom per unit cell by the number of unit cell. And the last step is to compare the packing efficiency of simple qubit cell, body-centered cell, and face-centered cell to understand how much space the atoms truly occupy in each structure.
The model can be used in schools, college, and university, or essentially any institution that teaches crystal structure or atomic packing. Since many students struggle with abstract 3D concepts, this model offers a practical or effective way to reinforce learning. In terms of mass production, the prospects are very promising. The model is made from simple and easily sourced material, such as plastic or acrylic bolts, polystyrene spheres, and Velcro tape. These components are inexpensive and widely available, allowing the model to be manufactured at low cost. This makes the cubic Crysta box highly cost-effective for educational use. Unlike digital simulations or specialized equipment, it is durable, reusable, and encourages hands-on learning, all while keeping production costs affordable.
The cubic Crysta box model received strong positive feedback during testing and evaluation. Expert validation reported a high validity index of 90.6%, confirming that the model is accurate and suitable for teaching crystalline structures. A total of 118 students who previously completed Inorganic Chemistry 1 SAT 3013 evaluated the model, and the results show consistently high usability scores, which are usability 95.2%, ease of use 95.4%, ease of learning 95.2%, and satisfaction 95.2%. Students reported that the model improved their ability to visualize 3D structures, making abstract concepts easier to understand and increased their overall engagement during learning activities.
For future improvement, we can improve the cubic Crysta box model by following these steps. First, material durability. Upgrade to more durable, eco-friendly, or higher quality material to withstand repeated classroom use. The second one, add-on modules. Extra components could demonstrate advanced concepts like crystal defects, twinning, or Miller indices, expanding the model's usefulness beyond basic cubic structures. The third one is expansion to other crystal systems. The modular design allows adaptation to tetragonal, hexagonal, and monoclinic. This will involve new box shapes and atom placement such as a hexagonal prism for hexagonal systems, while retaining the same hands-on learning approach.